In this video, we'll introduce analysis of an RLC circuit, a circuit with resistors, inductors, and capacitors. So this is Module 9, and our objectives here with the RLC circuit is to look at the natural response of series and parallel RLC circuits. So what we'll look at there is the damping factor, the resonant frequency, and understand underdamped, critically damped, and overdamped responses. And then we'll determine the complete natural and forced response of series and parallel RLCs. Now specifically, we're doing these for switched circuits, for circuits where we're switching on and off a DC source as opposed to a source that of alternating current that changes with time. So if we compare this to what we did in Module 8 with just RL circuits or just RC circuits, we can what we looked at with an RL circuit was just we looked at this as a series circuit, and we looked at an RC circuit as a parallel circuit. The inductance was a dual of the capacitance, and the series was a dual of parallel. So in our series circuit, we did a KVL equation. So our KVL equation was our VL, LdI plus our VR, IR, was equal to 0. So in here, we just divided to get this in proper form for a single order differential equation. We divided through by L. Whereas in our RC circuit, we did a KCL analysis where our IC was C dV dt and our IR was V over R. And again, we divided through by C to get our dV dt with a coefficient of 1. So with both of these equations, we assumed a solution. We assumed our solution for current is some arbitrary constant A times our exponential function e raised to the power of st, where s is a frequency and t is an instant in time. And similarly, we did that for our voltage solution for our RC circuit. In doing so, if we put that solution back up into our original differential equation, we came up with this characteristic equation, both the function itself and the first derivative of the function have an ae to the st in it. So our characteristic equation, s plus r over L in this case, is what must be equal to 0 to have a non-trivial solution. So our frequency, r over L, also is represented by our time constant tau L, which is 1 over the frequency, or L over R. And we got a similar solution with our RC, but with our RC, our time constant was the resistance times the capacitance, and both of these time constants are the dual of each other. So that's what we did with our RL and RC circuit. How did we solve for A? Well, to solve for A, we used the initial conditions to solve for A. So we'll do something similar with RLC circuits. We also then looked at if we had switched in a forced response, then we used the concept of superposition, where we said the current through this RL circuit would not just be equal to the natural response, A e to the st, but we'd add to that the forced response after the natural response has died out. So that natural response has died out means there's going to be no more changing with time, so the voltage across our capacitor will be equal to 0. And that's what we used to find the current at infinity, and our solution was I of infinity plus A e to the st. And again, we had to find S. We found our time constant after the discontinuity, and we found A with our initial conditions. And similarly, the dual of that, our RC circuit. So in our RLC circuit, we have to have now two energy sources. So with our RL or RC circuits, we just had our first order differential equation, homogeneous if it was not there was no forcing function. So we had one energy storage device, and that's what gave us the single order differential equation. If with both an inductor and a capacitor in a circuit, we'll have two energy storage devices. So we'll get either a single second order differential equation or two simultaneous first order differential equations, because we'll have two derivatives, right? So we'll have two different derivatives, a di dt and an integral or a dv dt in the same circuit. So what we'll do then, we're going to have to evaluate the arbitrary constants. There'll be two arbitrary constants, but we'll have two initial conditions. We'll have an initial condition for the voltage across the capacitor and one for the current through the inductor. And when we evaluate those initial conditions, we'll evaluate one directly and one we're going to have to use the derivative of the response. What we did show also in Module 8 was that if we had two inductors, for example, in a circuit, that we could not combine because these inductors are neither in series or in parallel, we could we would end up still with two different time constants. So we could find the two time constants. For example, if we kill L2, by killing L2, that means there's zero current. Zero current's an open circuit, so we'd see that L1 would only see R1 because this would be open. And similarly, if we killed L1 we'd open it, and L2 would only see R2. So those would be our two time constants. And we could use superposition. Our I1 of t was just going to be equal to that initial condition, whatever that initial I1 current is, e to the negative t over tau 1, and our tau 1 would be L1 over R1. R1 would be the only resistor that L1 sees when we kill L2. And similarly, our I2, I2 of 0, e to the negative t over tau 2. So then we could find the current through the switch here. I switch would be equal to our I1 plus I2 by KCL at this node here. And so that is going to be equal to our I1 of 0, e to the negative t over tau 1 plus I2 of 0, e to the, let's forgot the negative t over tau 2. And now these have different time constants, so these exponentials are raised to different exponents. So we would basically have the sum of two exponentially damped equations here. And so we would have to have two initial conditions, which we did. So we'll do something similar with the RLC circuit, and again, we'll either end up with a single second order differential equation or two simultaneous first order linear differential equations. And that's what we had here, was two simultaneous first order single differential equations. So when we do that, we'll evaluate two arbitrary constants, initial conditions for those responses. We had two initial conditions in the last example there. And then we'll also have to consider an initial condition for the derivative of the responses if we don't have just two L's or two C's. So that this RLC circuit is very important because it can also model other physical situations, so that the math involved that's applied to physical situations can also be applied directly to the suspension of an automobile system. So we could model the suspension of an automobile system with an RLC circuit. It could also, we could look at it to find the behavior of a temperature controller, for example, one used in growing semiconductor crystals. And another example would be an airplane. You know, the response of an airplane to the elevator and airline controls. Here you have two different energy systems. We could model that with an RLC circuit. And of course, then, you know, it's fundamental. Our RLC circuit analysis is fundamental to the future study of communications networks and filter designs, which we'll look at more next semester. So that's our introduction. In the next video, we'll look at some more examples.